Okay, so we are looking at the flywheel. And in this case, we want to understand the functions of a flywheel. We are not going to take time to start going back into explaining why we need a flywheel and going into the parts of it. Our focus is just what is the function. From there, we do the analysis, which is about the calculations that tell us about how energy fluctuates. Then the flywheel takes it over. Here, I need to emphasize that even if you are using, whether you decide to use a 4-stroke or a 2-stroke cycle engine, the function of the flywheel remains the same. As you can see in the picture, we have this flywheel and you have your engine there operating. And I think from what I can see, this looks like a V6. There will be some points where after the power stroke, there will be other strokes which may be expected to be idle. I mean, to remain idle. So those are the strokes that could be taken care of by the flywheel, which will absorb that kinetic energy and distribute it. So the main function is just for it to absorb the excess energy, then release it when there's a drop in the energy. Now, like we know the formula for kinetic energy is half mv squared. When we come to rotational energy, we're talking about half I omega squared. What this means is that you need to have this I, which is the moment of inertia. Then you also need to know at what speed is this rotating. Then you put them together. And this angular velocity must be in radians per second. The I is given by the general formula mk squared. But I also need to emphasize that the I is not like standard for every little shape. Sometimes you'll find specific values, specific formulas that are used for the same I, depending on the shape. But the general one is simply mass multiplied by radius of gyration squared. So mass in kilograms, the K, or in some books, they decide to use R, it is measured in meters. So put them together, you have your moment of inertia. In case you're looking for torque, torque is normally given by the product of that moment of inertia multiplied by the angular acceleration. Meaning this could be for a flywheel which is increasing the speed or accelerating. Sometimes it could also be decelerating. In this case, traditionally we're used to finding that this omega-2 is the final speed or the maximum speed. But in this case, we're using omega-1 to represent the maximum speed, then omega-2 to represent the minimum speed. Then the fluctuation in energy of that flywheel is going to be given by the difference in kinetic energies between the maximum speed and the minimum speed. So hence, we have that formula there. Now, this means that if you want, you can even factorize half I, then in the brackets you have omega-1 squared minus omega-2 squared. Then apart from fluctuation in energy, we also have the coefficient of fluctuation of speed. This is an important factor, and I think as we proceed, later on, we'll find that we're also going to come back to the same factor because it refers to the ratio between the change in speed and the average speed or the mean speed of your flywheel. The mean speed or the average speed, as the term may tell us, is just the average between the maximum and the minimum speed. So you add the two speeds, divide by 2. Then it gives you that mean speed. Then additionally, you also have another factor, which is the coefficient of fluctuation of energy of the flywheel. So this one is just the ratio between that difference in energy between maximum and minimum and the work done per cycle. So the work done per cycle is given by W. So once again, we're saying that you need a flywheel to absorb that energy, store it, and then release it so that your engine can continue running smoothly. And what we have here are some formulas that we use for the analysis of the performance of a flywheel in terms of that fluctuation in energy which takes place. So here we're going to look at two examples. The first example here says, the turning moment diagram of a two-stroke cycle engine shows the excess energy produced per cycle is 10 kilojoules. That's what it shows. And the speed of the engine is required to fluctuate no more than 2% of the mean speed of 800 revolutions per minute. Then the question is asking us to calculate moment of inertia of the flywheel and the coefficient of fluctuation of the speed. So first, you look at the data we've been provided with. The energy, the excess energy is like the surplus. To get the excess, you have to subtract the two values. In other words, it's already giving us the energy that you have at the end when your flywheel is fluctuation. Rather, we're talking about how this flywheel is fluctuating, the difference between the maximum kinetic energy and the minimum kinetic energy as compared by the two speeds that you have there. Now, there is a condition that we've been provided with here. It says 2% of the mean speed. That is a fluctuation, meaning the maximum is going up by 2%. And what you end up with is a scenario like this. We're saying you have your omega. Let me put my omega there, if I would be allowed to do that. Then I'll say, suppose I'm looking at omega 1, it will be that omega 1 or omega 2, I can even say comma 2 is equal to omega plus or minus, and I think plus or minus the speed. Like, in fact, we can even just make it smarter like that. Plus the fluctuation. Oh, sorry, let me make the speed fluctuation. That's it. If I need to find now the minimum one, I'll still say omega 2 is going to be given by the mean speed minus the same speed fluctuation. Then it ends there. So that is how you sort out the two. One of them, each one of them gives us what we want. Now let's go down to the working. If you look at our working, we have already established that the fluctuation of energy is 10 kilojoules. And when you convert this 10 kilojoules to joules, you just multiply by 1,000, then you have 10,000 joules. The mean speed is 800 revolutions per minute. So all you do is convert this 800 to radians per second. So we go back now to the formula. In this case, it's 2 pi n over 60. The n is the 800 that has been provided there. So then we can then safely say 2 pi times 800, then you divide by the 60. The answer we are getting is 83.776. With this answer, we are now ready to get the maximum and the minimum speed. Let's start with the maximum one. We are going to add 2% do this. What is 2% of 83.776? It's simply 2 over 100 multiplied by the same number we have there, which is 83.776. And the answer comes out as 85.452. I always say that these numbers have to be and are constantly updated. So if you feel that that number looks off, you can always bring it out so that we update. The minimum one, which is omega 2, we go back to the same. 83 minus 2% of this same number. Again, this is the answer you get at the end of the day. Going to the first one, we're looking at the moment of inertia of the flywheel. We're saying, let's review the formula for fluctuation of energy, looking at the information provided. The fluctuation in energy, if you substitute, you try to make sure you factorize these, the formula we had, this is what you have. Meaning that we are saying E, which is the energy, is equal to half moment of inertia. Then open the brackets, you have maximum minus minimum. Of course, they're supposed to be squared. So substituting, where there's E, I'll put 10,000 equals, then there's half. I, we don't know it. Then the big one is the one we found to be 85.452. The other small speed is 82.105. Of course, here, if you decide to use 82.1, it's all fine. Then we just do the substitution. When I worked out what was on the right, it gave me 280.778. The I is still there. The next thing is just to divide both sides by this 280. Then the final answer for my moment of inertia is 35.615 kg square meter. 35.615 kg square meter. Next, I proceed now to the coefficient of fluctuation of speed. This is the one we said is supposed to be the difference, the ratio between the difference in speeds and the mean speed. So the difference in speed between the maximum and the minimum divided by our mean speed. Check back your data, you'll find that our mean speed was found to be 83.776 radians per second. The two speeds are 85.452 and 82.1005. Hence, looking at your working, it will give you this scenario here. 85.452, take away 82.1005. The answer you get, divide by the mean speed, which was given as 83.776. And according to my calculator, the answer gave me this, 0.04. Then units I have on top are the same unit I have for the denominator. So in the end, the coefficient is a unitless quantity. It's a unitless quantity. It just remains like that because those units would just end up canceling themselves out. So from here, you've noticed we've already calculated, we decided to calculate for the speed, fluctuation, and there we have our coefficient. Now, the second question, it's an interesting one. It talks about a punching machine, which is being used to stamp out circular holes from a sheet metal. The machine is fitted with a flywheel of radius of gyration 0.8 meters and has a speed of 200 revolutions per minute just before the stamping of the beginning of each stamping. Then it is found that 4 kilojoules of work is required to stamp out each hole. And this energy is assumed to come solely from the flywheel. If the speed reduction during the stamping is not to exceed 10% of the flywheel, or rather 10% of the maximum, calculate mass of flywheel required. Now, the condition that you can already pick is that when the stamping action is taking place, the speed reduces by 10% of the maximum, meaning that speed that we've already been provided with, it's the maximum speed, because this is the speed at which this stamping machine is running before the action of stamping is instituted. So if we already have one, the biggest speed, omega 1, it means we're just looking for the other one, the minimum speed, which is omega 2. So first of all, looking at the question I've been given, my radius of gyration, 0.8. Then looking at the other one, which is 200, which I've been provided with, is not already converted in the required SI unit. So I have to convert it, because if I don't convert it, I'll get it wrong. It will be in revolutions per maybe second or something. But the correct one is to take it through the usual formula, 2 pi times the provided value in revs per minute, then divide by 60. And by way of emphasizing, we say that the reason you're introducing the 2 pi is to convert the revolutions to radians. Then because it's per minute, that minute is taken care of by this 60, which implies that suppose the speed is given in revolutions per second, this 60 must disappear. Your answer will just be 2 pi n, no 60. Then the next thing is, once you enter this in your calculator, it's supposed to give you 20.944 radians per second. The conversion has already taken place. So since you have omega 1, you're just looking for omega 2. Omega 2, you will now subtract 10% of what you've been provided with. So 10% of 20.944 is supposed to give us 2.0944. So when you subtract it from 20, the end result is 18.8496. Next, we already have the energy that is being absorbed, or the energy fluctuation, which is 4 kilojoules. This converted to joules gives us 4,000 joules, because kilo is 10 power 3, or simply 1,000. So that is our E. Next, we can now go back and use the formula that we're supposed to use. In this case, it's E is equal to half I, then omega 1 squared minus omega 2 squared. When you substitute in this formula, things look like this. The only unknown is I. And with I being the only unknown, you can now go ahead and work out your solution. On the right-hand side here, I decided to cross multiply by 2. If you multiply by 2 here, you have 8,000, whereas everything else on the right-hand side remains the same. Then in the end, this is what you have. 83.344 I is equal to 8,000. So divide now 83.344 into the 8,000. The result is 47.994. All right. Now, from there, we have I equals mp squared. So what I have, I'm looking for the mass. So I know that given the I can decide to make m the subject. All I have to do is just substitute and then proceed with the rest. In this case, I have the 47.994. Then that's the one I'm saying I will divide by 0.8 squared. I will divide by 0.8 squared. And once I do that, the answer that comes out is 75 kg. Now, let's get one thing there. Okay, already I can see there's the need for updating our value here, because 8,000 divided by 83, let me just write it over here. The 8,000, I'll just put it right here. 8,000, if I divide by 83.344. So 8,000 divided by 83.344. Okay. It is giving me 95.987. Okay, I think this one is supposed to be some mini typo error that took place there. So meaning I should be able to get the value of my I, and the value of my I is supposed to be equal to 95.9877. With this, I can proceed now to get my M, where I divide the same one by the value that I got earlier. In this case, I'm saying I is equal to the MK squared. Let me just try to do this so that the squared will come and set up properly. Then MK squared. So from here, I can find my M, where we are saying the value we found, which was 95.9877 divided by 0.8 squared. So once again, we're saying 95.9877 divided by 0.8 squared. The answer is 149.98. So 149.98. Now this is almost the same as 150. You can almost say, because this can almost be like 199. So the mass being taken as 150 kg, it's still okay. So that's our working there. Of course, I'm not forgetting here we had said this is MK squared. Of course, let me just, oh, it's because I didn't open up this. Right. Just move it a bit, just a bit there. Again. Okay, that's fine. All right, so with this, we have our mass, which again, we are saying this value, we are updating it, it's supposed to be 150 kg. The error is just here. When we divide here, we get 95.9877 instead of 47. So we update the answer to this other value here. When it comes now to torque, with the torque, we are now looking for alpha, because we already have the I. The I is the one we just from finding there. So to get the alpha, we say omega 1 minus omega 2 divided by the time. Our omega 1 is simply 944.9 18.944, rather. Our omega 1 is 20.944. Then we're subtracting 18.8496. Divide by the time, which is 5 seconds. Then we get our answer, 0.4189. Then comes T is I alpha. Our I is not this value you are seeing here, but this other one that we have up there. We're saying our I is actually 95.9877. So here I'll say, let me just put this. We're saying, therefore, my T should be equal to 95.9877. Then we're multiplying by the value for alpha, which is 0.4189. 0.4189. So 95.9877 multiplied by 0.4189. The answer is 40.21. So meaning that's our torque. Our torque is supposed to be 40.21. Torque is equal to 40.21 Newton meters. Newton meters. The other one small letter. All right, let me just put them here below so they look like, there we are. Okay, so this is how you analyze the fluctuation in energy of the flywheel. You can also calculate the torque. And the only idea is that despite having so many of those different values, but the end result can always be the same as long as you don't rush the data. You take time to find your data, and then you can proceed to the rest of the calculation. Our lesson can end here, and thanks a lot. Looking forward to the part 2. Before that, there's this exercise that I want you to look at. All the answers are already planted there for you to check your working. And it's only having 3 questions. We'll follow this up with part 2, which will just be focusing on the energy diagrams for the same flywheel. All right. So we meet till the next lesson.